right, you're given a sample of metal, and you know a few things about it. We know the atomic mass is 43.1 grams per mole, the density is 6.4 grams per centimeter cubed, the atomic radius is 0.122 nanometers, and you're asked to find what structure it is. So most metals are going to be cubic or maybe hexagonal close packed, but what we do know about these different metals is that if we can figure out the packing factor, the volume of hardball sphere atoms divided by the total volume of the crystal, we can know what kind of structure it is. So that's what we want to do. We want to find the packing factor. So from these data, we want to figure out the packing factor. That's our goal. Well, so the packing factor is going to be the volume of atoms divided by the volume of the crystal. So we have enough information here to figure that out, but it pretty much turns out to be a dimensional analysis problem, and that's one of the things you'll find in material science, that there's lots and lots and lots of dimensional analysis. So what we need to do is think about atoms and volume. This density gives us the mass per volume for the crystal. We know that this is going to give us the number of atoms per mass, and actually this is mass per atom, because we know that there's Avogadro's number of atoms in a mole. So, and we've got the radius here of the atom, so we should be able to figure this out. If we have to think about finding the volume of atoms and their hardball spheres divided by the volume of the crystal. So now it's just a matter of thinking through this problem in terms of the units. So we know that there are 6.02 times 10 to the 23rd Avogadro's number atoms in a mole, and we know that there are 43.1 grams in a mole, so we're going to say there's 6.02 times 10 to the 23rd atoms divided by 43.1 grams. Now we can look and see where grams appears again in our data, and that's in this density, and that actually gives us the mass per volume of the crystal, which is something that we can use. So we have to be really careful that we get our data in there properly, but we can say, okay, well, we now know that we have 1 centimeter cubed in our crystal divided by 6.4 grams, and now we've got 1 over gram, that's going to turn out to be 1. So now we have the number of atoms per crystal, and so atoms per volume of crystal, and so now we just need to find the volume of the atoms. Well, if we assume they're hardball spheres, their volume is 4/3 pi r cubed, so we have 4/3 pi, and now we want to use our radius, but we want to make sure that we use the right units. We've got centimeters cubed here, so we want to convert this to centimeters. This is going to be 0.122 times 10 to the minus 7th centimeters. So 4/3 pi times 0.122 times 10 to the minus 7th centimeters. I want to cube that guy. Now we've got centimeters cubed in the top, centimeters cubed in the bottom, and this is per atom. Atom and atom, all the units cross out, which is what we want, and if we crank through those numbers, we get that this is 0.68, and the only system that has this for its packing factor is BCC. So our system is a BCC system.